Okay, it's great pleasure to have some crew from Cambridge. Thanks for waking up so early at the England. So he's going to tell us about the hemisphere blocks and the 3D n=4 gauge theory, please.
Great, yeah. Thanks a lot for inviting me. I'm going to talk to you today about these things that we're calling hemisphere blocks of 3D n=4 gauge theories. And a lot of what I'm going to say today is based on these three papers and ongoing collaboration with Matthew Bullimore, Nick Dorey, and Dan Zhang. So hopefully, yep. So before we start, just some background and motivation. So in supersymmetry, there's many examples of interesting extended algebras acting on the BPS states of the theory. For example, the AGT correspondence tells us that in some cases there's conformal algebras acting on BPS states. The gauge beta correspondence tells us that in some cases ground states for supersymmetric field theory have a quantum group action. And these phenomena can often be interpreted in geometric representation theory as quantum group actions on homology K-theory or elliptic homology of, for example, quiver varieties. And often supersymmetric indices or partition functions realize characters of these algebras. So today I'm going to talk to you about this kind of phenomena in three-dimensional gauge theories. And I'm going to discuss the action of quantized coordinate rings acting on boundary conditions for these theories. And in 3 dimensions, we have this extra ingredient of 3D mirror symmetry, or what mathematicians call symplectic duality. And I'm going to discuss some implications of that to our setup as well. Now, another big piece of motivation for this work is holography. So some 3D CFTs are dual to supergravity in 4 dimensions. And in many examples, indices of these theories have been shown to exhibit some exponential growth of states that accounts for certain black hole entropy or black hole microstate counting. And a lot of the motivation for this work is to make some steps towards understanding the geometrical content of this correspondence on the field theory side. Okay. So this is an outline of what I'm going to talk about. So I'm going to start with a quick review of 3D n=4 gauge theory, just to set the scene and fix the notation. Then I'm going to discuss the quantized Higgs and Coulomb branch algebras of these theories and how we build modules from boundary conditions. And I'm going to talk mostly about Verma modules and the exceptional Dirichlet boundary condition, which I'll define properly later. Then we're going to compute hemisphere partition functions for these theories and show that they realize holomorphic factorization for closed 3-manifold partition functions. And I hope to demonstrate these ideas with some concrete examples and show you some applications. I'm also going to talk about the twisted index in particular and how the twisted index can be factorized into hemisphere partition functions. And I'm going to discuss the geometrical implications of this factorization in terms of Poincare polynomials of vortex moduli space. I hope finally that there'll be time to discuss these ideas in a particularly rich example called the 3D ADHM theory. So that's the 3D gauge theory described by this ADHM quiver. And most of the examples starting the talk are going to be quiver varieties, so that yeah, some examples of these here. And yeah, do feel free to stop me throughout if there's any questions. Okay, so I'm going to be talking about 3D n=4 gauge theories that preserve 8 supercharges. And they're going to be uniquely specified by fixing a gauge group, G, and representation for the matter. And the theories that we consider are going to be constructed in the UV out of familiar n=4 vector multiplets, the scalar components of which I've written there, and n=4 hypermultiplets whose scalar components we're going to write x and y throughout. These theories have a non-abelian R symmetry, SU2H times SU2C, which acts on the hypermultiplet and vector multiplet scalars respectively. And they may also have global symmetry GH acting on hypermultiplets, and GC, which in the UV is an abelian symmetry rotating the dual photons, but generally will be enhanced to non-abelian symmetry on the Coulomb branch in the IR. We're also going to turn on generic. I'll explain a bit more what I mean about generic later, but we're going to turn on generic masses and FI deformations for the global symmetries GH and GC. Throughout, we'll also turn on this deformation T. There's going to be a background Vev for an anti-diagonal R symmetry combination, and this T deformation is sometimes called softly breaking the supersymmetry to n equals 2 star. Okay. So generally, these theories have a non-trivial moduli space of vacua. This splits into two distinct branches called the Higgs branch, where hypermultiplet scalars obtain a Vev, and the Coulomb branch, which is parameterized by vector multiplet scalars and monopoles. Now, the Higgs branch is described purely classically, so it doesn't receive quantum corrections and can be described just by minimizing the classical potential in the Lagrangian. And this leads to a hyperkähler quotient construction of the Higgs branch. Whereas generally the Coulomb branch is intrinsically non-perturbative and is generated by monopole operators. And these two branches of vacua are exchanged by 3D mirror symmetry, as we'll meet in more detail later. Generally, supersymmetry constrains both these moduli space branches to be hyperkähler manifolds. And the global symmetry GH cross GC will act as a tri-Hamiltonian isometry on each of these branches. Now, it's an assumption throughout this work that our theories flow to conventional superconformal fixed points. So we're going to assume that the theories are good or ugly in the Gato-Witten classification of 3D SCFTs. And we're going to assume that it's possible to turn on mass parameters that lift the Higgs branch to isolated massive vacua and resolve the Coulomb branch. And likewise, we're going to turn on generic FI parameters that fully resolve the Higgs branch and lift the Coulomb branch to isolated vacua. So precisely this means that the Higgs branch and the Coulomb branch are going to be a pair of symplectic resolutions with isolated singularities. Okay. So most of the examples that I'm going to talk about today, well, all of the examples I'm going to talk about today are going to be quiver gauge theories. So these are 3D n equals 4 gauge theories specified by a quiver diagram. So for each node in a quiver, you have an n equals 4 vector multiplet, and lines represent hypermultiplets. So our favorite example is going to be SQED with n hypermultiplets. So we have n fundamental hypers here, xi, yi, which gives us an SUN flavor symmetry. There's a U1 gauge group. And the Higgs branch of this theory is described by this Nakajima quiver variety, which is the cotangent bundle to Pn minus 1. And we're going to turn on generic masses that give us n isolated vacua. So geometrically, these n vacua are just which coordinate of Pn minus 1 you set to be non-zero. Okay, so this is one of the main examples we're going to discuss today. And one of the other main examples is the TSUN theory. So this is a theory whose Higgs branch is the cotangent bundle to a complete flag variety. And it has a non-abelian product gauge group. And GH equals SUN flavor symmetry and SUN topological symmetry. And in fact, as we're going to see later, this theory is self-mirror dual. So the Coulomb branch of TSUN is also cotangent bundle to the complete flag. And if we turn on generic mass parameters and generic FI parameters, then the vacua of this theory are labeled by elements of the permutation group. Later, I hope, if there's time, we're also going to meet this 3D ADHM theory, whose Higgs branch is described by the ADHM moduli space. But I'll discuss that in more detail when we come to it. Okay. So now I'm going to discuss the Higgs and Coulomb branch algebras of these theories. So if we fix a particular n equals 2 subalgebra, so we select a U1 cross U1H cross U1C out of the non-abelian R symmetry, then this corresponds to fixing a complex structure on the Higgs branch and the Coulomb branch, and selects particular supercharges QH or QC, whose cohomology gives a ring of chiral operators that we call Higgs branch operators or Coulomb branch operators. And geometrically, these are rings of holomorphic functions with respect to our particular complex structure on the Higgs branch or the Coulomb branch. Now, the imprint of hyperkähler geometry on these rings is that they come equipped with a holomorphic symplectic form. So you compare the holomorphic functions and give these rings a Poisson bracket structure. Now, in this talk, we're going to put our theories on a flat space-time with a boundary condition in the plane, and we're going to place theory in an omega background. So there's a number of different ways of realizing this omega background, but however you do it, it deforms the supercharges QH and QC such that they square to the action of rotations in the plane, so that we're working equivariantly with respect to rotations in a fixed axis. And what this means is that the operators, so the Higgs branch operators or the Coulomb branch operators, are now forced to lie in a line along the axis. And this introduces a notion of operator ordering. So the rings of chiral operators are no longer commutative. And geometrically, this corresponds to a deformation quantization of the Poisson bracket structure on the rings of holomorphic functions. Okay. So just so that we have something concrete to look at, I've written down here the quantized Higgs branch algebra and the quantized Coulomb branch algebra for the SQEDN example. So on the Higgs branch side, you have n hypermultiplet scalars, xi and yi. The Poisson bracket is canonically quantized to this commutation relation. And then the algebra is generated by gauge invariant operators in x and y that satisfy the quantized moment map constraint. And it's possible to show that this algebra is a central quotient of SLN. Later in the talk, we're going to construct Verma modules for this algebra. On the Coulomb branch side, the algebra is generated by a complex scalar and monopole operators, and the algebra structure is determined by it was determined in this work by Laumon, Demofte, and Galotto, called the Coulomb branch of 3D n equals 4 gauge theories, and the commutation relations are given here. And this is what mathematicians call a spherical rational Trednik algebra, or a very simple finite W algebra. Okay, we'll come back to these algebras later when we construct modules. Okay, so we've discussed half BPS Higgs branch operators and Coulomb branch operators, but these theories typically also exhibit half BPS vortex solutions. And in fact, the Hilbert space of the omega deformed theory in the plane coincides, well, when we turn on mass deformations, coincides with the equivariant homology of the moduli space of vortices. So there's a relationship between vortices and quasi-maps, so which I'm going to explain in this slide. So first of all, if you have a vortex in the plane, then at infinity, the hypermultiplet scalars have to go to a point in the Higgs branch. And if you turn on masses, then the hypermultiplet scalars at infinity have to go to a fixed point of the Higgs branch under the flavor symmetry. And the vortices come in distinct topological sectors labeled by vortex number, or this second Chern class here for the bundle associated to x and y. And so you have a natural identification with quasi-maps coming from, if you compactify the plane, then you have maps from a sphere or from a P1 where the infinity maps to a specific vacuum, and the image of the map is described by this homology class. And these moduli spaces can be given an algebraic description as the quasi-map moduli spaces of Kunkov and others. And these are Kähler manifolds that come equipped with certain group action. So you have a fugacity Q corresponding to rotating the the domain of the quasi-map, and you have you have another symmetry GH coming from the Higgs branch global symmetries. And generally, again, you have isolated fixed points on this quasi-map moduli space. The object that we're going to talk about in this talk are the k-theoretic vertex functions of these quasi-map moduli space. So these are roughly something like an analog of a chi-t genus of these moduli spaces. And in fact, in some cases, they're exactly chi-t genera. Okay. So again, for something concrete, if we talk about this 3D n equals 4 gauge theory, so it's described by this quiver, and the Higgs branch of the theory is the cotangent bundle to a partial flag variety. And in this case, the vortex moduli space can be described by the space of quasi-maps from P1 into the flag variety. And Nakajima shows that these quasi-map moduli spaces coincide with Handsaw quivers. So this is a Handsaw quiver variety, and the vortex number are specified by the gauge notes. So these D here are the particular vortex number, and the rho I here specify the rho of the T rho theory. And later we're going to compute chi-t genera of this space and also discuss Poincare polynomials and what those invariants mean physically. And this is a particularly nice case because the Handsaw quiver, also known as a Laumon space, is a smooth variety. So just a complex manifold. Okay, so a more complicated example of a quasi-map moduli space that, as far as I know, cannot be given a simple quiver description is the moduli space of vortices for this 3D theory. So this is 3D ADHM theory with one flavor, and the Higgs branch of this theory is the Hilbert scheme of endpoints in the plane. And so I can't write down a quiver description of this vortex moduli space, but one can still understand the fixed points and the virtual tangent bundle, virtual structure sheaf, and compute the k-theoretic vertex function, as we're going to do later. Okay, so the main thing that we're going to compute in physics in this work is the hemisphere partition function for a particular theory. So yeah, it's a partition function on a hemisphere, and there's a torus boundary. So we have to specify an n equals 2 boundary condition on this torus. Now these kind of partition functions, dispartition functions, have been computed for a variety of different boundary conditions. As we'll see in a moment, we're going to consider a particular boundary condition called exceptional Dirichlet. But this paper by Yoshida and Sugiyama considers a Neumann boundary condition, and they localize the hemisphere onto the Coulomb branch, and they show that the partition function decomposes into some classical one loop and contributions from vortices in the theory. We're going to slightly modify that prescription to a different boundary condition, and in general, again, we expect that we receive some classical contributions, one loop, and some vortex contributions. And it would be interesting to sort of derive that expectation using some Higgs branch localization scheme on the hemisphere, which, as far as I know, has only been carried out for closed three-manifold partition functions. Okay. So, in fact, I want to make the link to representation theory manifest. So instead of computing a hemisphere partition function, I'm going to count local operators inserted at the origin. And we expect there to be a state operator map between the partition function on the hemisphere and the count of local operators inserted at the origin of the boundary. And typically these two objects are related by some kind of Casimir energy term. And that's exactly what we're going to find in this talk. So the half index is the object that counts these operator insertions, and it just counts the operators graded by various symmetries in the theory. Okay. Right. So there's a lot of information on this slide, but I'll pick out the important points. So the boundary condition that we're going to put on the plane is called exceptional Dirichlet. And the point of these boundary conditions is that they're associated to isolated massive vacua on the Higgs branch. So yeah, first of all, we choose Dirichlet for the vector multiplet. And in particular, this is going to mean that we're going to have a sum over boundary monopoles, because monopole operators are compatible with this boundary condition. Secondly, we need to say what we're doing with hypermultiplets. So we choose a Lagrangian splitting of the hypers, and half of them are set to Dirichlet and half of them are set to Neumann. And in particular, this is different, or can be different, from the canonical splitting associated to a cotangent bundle. And in fact, we want to take various different splittings. And then we deform some of these scalars to a constant value. And we make these choices in such a way that the gauge group is fully broken, but a maximal torus of the Higgs branch global symmetry and Coulomb branch global symmetry is preserved. And furthermore, we want the image of this boundary condition to coincide with a Lagrangian submanifold, or the attracting submanifold associated to a fixed point. Okay, so once you fix a chamber, on the Higgs branch, you can consider at each vacuum, you've got some attracting directions and some repelling directions. And if you follow the attracting directions, you sweep out a Lagrangian submanifold associated to each fixed point, which I'm calling L alpha. And this boundary condition is engineered to coincide with that submanifold. Okay, good. Given that data, there's a recipe to compute half indices for these theories. So we specialize the recipe of De Moffat, Garter, and Paquet n equals 4 theories. And yeah, so it has some contributions from some perturbative contributions from the vector multiplet, a sum over boundary monopoles, and then contributions from boundary hypers, depending on the splitting that we choose. And so the point of doing this is that we want to give a UV boundary condition prescription for a partition function associated to these isolated massive vacua. And we'll see that this realizes factorization of closed 3-manifold partition functions.
I have a question.
Yes, yeah.
So you said the Lagrangian splitting of hyper can be the choice of Lagrangian submanifold in Higgs branch?
Yeah, so this Lagrangian splitting is before you take the gauge group quotient. So you have to choose a splitting for your quiver such that when you take the quotient, the image of that splitting is this Lagrangian submanifold.
Mm-hmm. Okay.
And in general, yeah, that's tricky to find. So I've only done that explicitly for SQED.
I see. But this alpha is the choice of something. Yeah,
alpha parameterizes the fixed points on the Higgs branch, or the vacua.
Okay.
And associated to each fixed point, you have a certain submanifold of the Higgs branch that comes from, each fixed point, once you choose a chamber for the masses, then the tangent space at each fixed point splits in half. So you have some attracting directions and some repelling directions. And if you gradient flow outwards from those fixed points, then you flesh out a Lagrangian submanifold.
I see.
And yeah, the image of this boundary condition should coincide with that submanifold.
Okay, so and this twisted index, or what? Half index, also depends on the choice of alpha.
Yes, definitely. Yeah. So you have a half index for each vacuum. Yeah, that's a key point. Yeah.
I see.
Exactly.
Okay, thank you.
So yeah, you have half index associated to each massive vacuum. Okay, again, sorry, this is quite a busy slide, but I'll highlight the important bits. So just to show you the construction explicitly for SQED. So I here specifies our particular fixed point, our particular vacuum, and it runs from 1 to n. So yeah, for each I, there's a different Lagrangian splitting and a different half index or a different operator count. So yeah, some points here are that first of all, you write down the Dirichlet half index. So before we deform to these particular constant values, you have an unbroken flavor symmetry. So I mean, the gauge group is completely broken to a flavor symmetry on the boundary. And before you deform these constants, you have a fugacity for that, in this case, for the U1 boundary flavor symmetry. We have the usual sum over monopoles, the vector multiplet contribution, and then these contributions from the hypers. So the numerators Neumann and denominators are Dirichlet contributions from here. And then the main point I want to highlight on this slide is that when you compute an exceptional Dirichlet boundary condition, so deformed to this particular constant value for some of the scalars, then the recipe tells us to specialize the fugacities corresponding to the chiral that breaks this particular combination of flavor gauge and R symmetries. And the main point I wanted to make is that if you're familiar with how you typically compute enumerative invariance of quiver varieties, then this specialization is nothing but evaluating the churn root of a particular bundle at a fixed point. And as we'll see later, this half index procedure can be given a transparent geometric interpretation as computing a particular normalization of a K-theoretic vertex function. And this is precisely a churn root evaluation. Okay. So this is the end result of the half index computation. You have a classical term, which here I'm lifting from the hemisphere localization, which I'm not talking about today. The index contributions are one loop piece and a vortex piece. And for this theory in particular, the vortex moduli space is a nice, simple Handsaw quiver. And it's relatively straightforward to see that the vortex contribution to the half index coincides with the chi-T genus of this Handsaw quiver. So the chi-T genus can be computed by localization. In fact, this Handsaw is just flat complex space. It's C to the mn, where m is the particular vortex number and n is the number of hypers. And there's one fixed point at the origin. So the chi-T genus receives one. Was there a question? Sorry. No. So the chi-T genus receives a contribution from the one fixed point, this term here. Okay. Yes. And the one loop piece you can think of as a particular normalization of the chi-T genus of the vortex moduli space. Okay. So why are we talking about exceptional Dirichlet boundary conditions? I think I already mentioned this in the last slide a bit, but yeah, the idea is that this is a set of boundary conditions that are canonically associated to isolated vacua. And we expect in general that these boundary conditions flow in IR to thimbles in the sigma models, thimble boundary conditions. Another reason is that, well, it's a general principle that when you have a boundary condition, you can construct a module for the quantized Higgs and Coulomb branch algebras. So the way that works is you fix a local boundary operator here. Then when you bring a bulk operator to the boundary and act on the boundary operator, this gives you a module structure. And in this paper by Bullimore, Dimofte, Gatto, and Hilburn, mirror symmetry and symplectic duality, they show that in general, you expect exceptional Dirichlet boundary conditions to yield Verma modules in this way. And we're going to show that the Casimir energy term can be thought of as kind of an equivariant vacuum energy and gives the highest weight of these Verma characters. And in general, the whole hemisphere partition function in a specialized limit gives a Verma module character. Okay. Yeah, so as I sort of mentioned before, the whole hemisphere partition function calculation can be abstracted geometrically, and in fact can be described solely in terms of Higgs branch data. So the input to compute this hemisphere block is quiver variety. So in this example, we've got two gauge nodes and two flavor nodes. And associated to each gauge node, you have a line bundle, which I'm calling L1 and L2. So these are tautological line bundles over the quiver. Now you also have to pick a chamber. So the hemisphere blocks are defined with respect to a particular chamber choice. And if you change the chamber, then you expect wall crossing of the blocks. So physically, this chamber choice is an ordering on our mass parameters. So for SQED-N, yeah, here, for example, we choose the mass parameters ordered in this way. And in terms of the quiver variety, this is like choosing a particular C star action out of the global isometry group. And once you make this choice, at each fixed point, you've got some subspace of the tangent space called the attracting directions that I'm labeling by N alpha plus. And this space enters the definition of the block. So the partition function also depends on a chamber for the Fi parameters. Geometrically, this is a choice of stability parameter for the quiver variety. So there's a fire alarm going off in my. Hopefully it will stop.
Can I ask a question? Simple question.
Yeah.
In this QED case, when n equal to 2, I think Higgs branch is T star CP1, right? CP1.
Yeah, that's right.
Yeah, in that case, I think it's self-mirror, right?
Yeah, exactly. Yeah.
Then even quantization, Coulomb branch or Higgs, in both cases will lead to SL2.
Exactly.
SL2 Lie algebra.
Exactly.
In that case, what is the Verma module is just some these discrete series of the SL2 or
yeah, exactly. I'm actually gonna write down this example explicitly.
Later. Okay.
I'm gonna do TSU2 exactly. So maybe we can go over it then maybe.
Oh, okay. Then I'll wait.
I'm gonna apply exactly the recipe to T star P1. It's the simplest example.
Oh, yeah. Okay. Then and also the buzzer stops. So go ahead.
Yeah. I think we're okay. Okay. Good. Yeah. So the definition also depends on a chamber for the Fi parameters. The way this enters in the definition is that the vortex moduli spaces change if you change the Fi parameters. The ones that are non-empty change. Okay, so given that data, you can write down the hemisphere partition function. So there's a classical piece, this Casimir energy piece, which is determined by characters of line bundles over the quiver, and a piece corresponding to the attracting directions. When I write N alpha plus, I just mean the character of that tangent space at that point, or that space at that point. There's a one loop piece, which is essentially just a platistic exponential of the same subspace, the tangent space. And the V here is the K theoretic vertex function of the associated quasi-map space to this quiver. And as we've seen in some cases, you can realize that vertex function is just a chi-T genus of the vortex moduli space. Okay. So yeah, now I want to talk about Verma characters. And these arise in two specialized limits of the half index. So we call these limits the B limit and the A limit. And these limits restore n equals 4 supersymmetry. So in both cases, well, I mean, in the B limit case, you have an extra supercharge that means that the index receives contributions only from Higgs branch operators, and consequently only one loop contributions survive in this limit. And so, yeah, in the B limit, you're just tracing over boundary Higgs operators. And conversely, in the A limit, the extra supercharge that you get tells you that this index traces over Coulomb branch operators, so boundary monopoles. And in that case, only the vortex contributions survive. So if I just go back to the last slide, this is the one loop piece. So in the A limit, only this piece survives. And in the B limit, a particular degeneration of the vertex function survives. Okay, good. And yeah, the Casimir energy term also has a well-defined B limit and A limit, and we'll see that this gives us the highest weight of the Verma character. Okay, so this is the example you asked me about, the TSU2 theory, which is self-mirror dual. So I'm focusing here on the Coulomb branch side. So in the top right, I've written the Coulomb branch algebra explicitly for this theory. And the Verma module is generated by a highest weight state, which I'm calling B alpha. And it's annihilated by the V plus monopole operator. And you can read off the highest weight charges of that state from the fact that this relation annihilates B alpha plus. And so to build the Verma module character, we trace over this module, or we lower with V minus, and trace over this module weighted with the Cartan phi hat. Okay, so those are the Verma module characters. You can compute the half index using the method that I've described. And you have two of these because you have two vacua. And you can see here that this is the Casimir energy term. And you can see that this term corresponds with the eigenvalue of phi hat here. So you have an M alpha corresponding to X and a half corresponding to this epsilon 2. And then this geometric series is just what you obtain by lowering with V minus, the V minus monopole operator. And yeah, geometrically, this A limit degenerates the chi-t genus to just a count of fixed points. So yeah, the chi-t genus can be computed by some fixed point localization. And when you take, with numerators and denominators, and when you take, well, yeah, this expression here, and when you take t goes to q to the half, it just becomes 1. So it counts the fixed points on the vortex moduli space. Okay. So yeah, just to recap what we've seen so far. So I've discussed how to compute hemisphere partition functions and half indices of this particular class of boundary conditions that are associated to fixed points. And in fact, the recipe is determined entirely by geometry of the Higgs branch. And then we've argued that certain specialized limits of these objects give us Verma module characters of the Higgs branch or the Coulomb branch algebras. So that's summarized succinctly in this expression here. So you take your hemisphere partition function, and then you have two limits that give you either the Verma module character of the Higgs branch or the Verma module character of the quantized Coulomb branch. Okay. Are there any questions at this point? Okay, good.
So character is something like a 1 over 1 minus x in this example.
Yeah, exactly. Yeah, 1 over 1 minus c here for the Coulomb branch.
Oh, okay. I see.
Yeah, exactly. It's a really simple character for TSU2.
Oh, okay.
We're gonna hopefully for the time we'll see a more complicated example later with the Hilbert scheme of points.
Okay, thanks.
Okay, good. So now I'm going to talk about holomorphic factorization. So starting with the work of Sarah Peschetti, the certain three-manifold partition functions were shown, or the three-sphere partition function in particular, was shown to factorize into a set of blocks, which I'm calling B alpha here. This has been extended in many directions since, so many examples like the twisted index, the squashed ellipsoid partition function, or the superconformal index, they all, in many examples, factorize into the same set of, for a given theory, there's a set of holomorphic blocks, and these three manifold partition functions factorize into a product of, or sum over vacua of a product of these blocks. And a systematic approach to understanding this factorization is the holomorphic blocks of Beam, de Moffat, and Peschetti. And so these blocks are sort of determined, or essentially determined by a set of Q difference equations, and at least their non-perturbative part coincides with these vertex functions that I've been talking about. And so the way to decompose the three-manifold partition function is that you split it along a boundary torus, and then you have different gluings corresponding to this decomposition of the three manifold. And the way the gluing acts is by an SL2Z transformation on the fugacities of your blocks. So what I'm going to argue in this talk is that the hemisphere blocks that I've written down exactly factorize the various three-manifold partition functions. So often the way that this is demonstrated is that you localize a partition function to the Coulomb branch, and then you show that it factorizes into a sum over vacua of some perturbative piece, and then a vortex and an anti-vortex piece. And in fact, there's no ambiguity in the hemisphere block definition, and it exactly factorizes this perturbative piece in this way. And we've shown that explicitly for super QED and the ADHM theory. I mean, in particular with the holomorphic block prescription, you can add, because they're sort of determined by Q difference equations, you can add things that are Q constant, and there's some ambiguity in what the perturbative piece should be. Okay. So one sort of immediate application of this is that you can glue together these hemisphere blocks, and then you can take the specialized limit to get a Verma character, and then then we can show that various three-manifold partition functions in this n=4 limit decompose as the sum of Verma characters. So for example, the three-sphere partition function can be written as a sum over Higgs branch characters and a sum of Coulomb branch Verma characters. And this was made as
Can I ask a question? So you said that in the hemisphere partition function there is no ambiguity, whereas in the blocks there is this Q constant ambiguity. So, but I mean, so that means that for you, you can give a physical meaning to this Q constant, which is something which has has a trivial semi-classical limit. So how can you give a physical interpretation to this object?
So for me, I think this Q constant is simply the Casimir energy term that relates the half index to the hemisphere partition function. So
then I don't agree. This is not what we call the Q constant. We also have this gadget that you call Casimir energy, and that one is not a Q constant. So the Q constant is something that is transparent to the difference operator that acts on the block and has a trivial semi-classical limit. So it's really something that, I mean, for us, we could indeed not determine, but it disappears when you glue blocks into something compact. And it is not the Casimir energy, which instead we also need to factor out the gluing. So I'm not sure that it's possible to give a physical interpretation to the Q constant. So I don't know. I mean, maybe I think what you do in the hemisphere, somehow you just end up with a choice of that constant. I don't think you can give it.
Yeah, maybe that's a better way to phrase it. I think
I don't know.
Once you fix a boundary condition on this hemisphere, you don't have any choice anymore. The normalization of the partition function is fixed. I suppose that's what
I mean, it's like for us, your boundary conditions, they're like in one-to-one correspondence with the BPS vacua, which are also the vacua which label our solutions. And we're always free to multiply our solution by Q constants. So indeed, I mean, you can multiply by them, but since they have a trivial semi-classical limit, they don't affect the choice of the vacuum. So that's
Okay, it'd be good to discuss this a bit more afterwards, actually.
Sure. Thank you.
Yeah, that's interesting. I guess in this setup we don't really see. There's no choice of Q constant, I suppose, in a way. Okay, good. So how are we doing for time? So the one application I want to talk about is to A and B twisted indices. So these can be realized as partition functions on a twisted product of S2 times S1 with a background R symmetry flux. And there's two twisted indices you can consider either twisting by the Higgs branch R symmetry or the Coulomb branch R symmetry. And in many cases, the A and B twisted indices can be factorized into a sum of holomorphic blocks, and the particular gluing is just the fugacity Q is inverted in each of the blocks. Geometrically, we can show that this particular gluing can be interpreted as factorizing the chi-T genus of this global quasi-map space or global Laumon space. So this means I don't fix a particular vacuum at the north and south poles. And this chi-T genus factorizes into a sum of chi-T genera of local vortex moduli spaces. And now it turns out that actually this Q is an exact deformation of the twisted index. So the twisted index doesn't actually depend on Q. And from this geometrical perspective, that's because, this arises since the global Laumon space is compact, and the chi-T genus of a compact space can't depend on global symmetries. So in fact, it's also independent of, well, the A index will be independent of X, and the B twisted index will be independent of C also. Okay, yeah, so since...
Can I ask a question?
Yes, yeah.
Is this chi-T genus coincide with Hilbert series? Sorry, I just got...
not quite. So the chi-T genus is like, yeah, it's like a generalization in some sense of the Hilbert series. So okay. The Hilbert series counts holomorphic functions over the moduli space.
Yeah.
And the chi-T is like a trace over Dolbeault cohomology. So it includes, okay. Includes holomorphic functions plus holomorphic forms as well.
Okay.
And at least for non-compact spaces, you can localize this to a sum of fixed point contributions. And it looks like a Hilbert series, but with a numerator as well.
Okay. So to get as far as I remember, to get a chi-T, you need to compute S1 cross sigma G instead of like S2. Anyway, I may be wrong. Sorry. As far as I remember, S1 cross S2 correspond to Hilbert series of Coulomb branch or Higgs branch. I may be wrong. Sorry.
No, you're right. Yeah, the A and B twisted index will compute the Hilbert series of your Higgs branch or the Coulomb branch, but it factorizes. Yeah, no, you're right, but this is a different space. So basically, yeah, essentially the Hilbert series of the, let's say, A twisted index will coincide with the chi-T genus of the modular space of vortices to the Higgs branch.
Okay, that's what you mean. Okay.
Yeah.
Okay,
exactly.
thank you.
Okay. So since the index is independent of Q, then we're free to send Q to 0, for example. So it'd be interesting to look at the Q to 0 limit of hemisphere partition function. So in some nice cases, so these cases where the Higgs branch is, say, a cotangent bundle to a flag variety, then the vortex moduli space is a smooth variety, and in fact a resolution of singularities. And this Q fugacity is conjugate to a group action that contracts us to a compact submanifold of the vortex moduli space. And in that case, sending Q to 0, well, first of all, sending Q to 0 in the one loop piece is fairly innocent, as you can see here. It just reduces us to the plastic exponential of T times N alpha. And in the vertex function, we're sending Q to 0 in a chi-T genus. Which, as I said, will compute the chi-T genus of the compact core of the vortex moduli space. And since that's compact, then the chi-T genus, in fact, coincides with the Poincare polynomial. So the upshot is that essentially the Q0 limit of hemisphere partition functions are Poincare polynomials of vortex moduli space. Okay.
Sorry, what is pi here? Pi.
Oh, sorry. Yeah, pi. I should have explained that. Yeah. So I'm thinking here actually in terms of Handsaw quivers, which are resolutions of singularities. So pi is my resolution of singularity, and an unresolved quiver variety, there's a single fixed point.
I see.
Yeah, this pi is the inverse in the resolved space of that fixed point.
I see.
Which is compact. And Q is a fugacity that takes us from the whole vortex moduli space down to this compact core. I've been a little bit vague about how general this applies because I'm not sure. So I mean, the Q zero limit is always well defined. Well, provided you're talking about good or ugly theories, or what mathematicians call large frame vanishing, then the Q zero limit of the vertex function is well defined.
I see.
And it has a nice transparent geometric interpretation, well, at least for me, in the case of cotangent bundles to complete flags, where it gives us Poincare polynomials.
Pi is more like a Hilbert-Chow map.
Yes, exactly.
I see. Okay.
Yep. Okay, good. So yeah, as you said, the twisted index computes the Hilbert series of 3n equals 4 theory, and the A twisted index computes the Coulomb branch Hilbert series. So first of all, we factorize the Coulomb branch Hilbert series into a sum of blocks, and then we're free, for example, to send Q to 0. And in that case, you have, from the argument in the previous slide, the non-perturbative contributions become generating functions of Poincare polynomials of Handsaw quivers. And in fact, the perturbative contribution, I haven't really gone into the details of this, but the perturbative contribution gives us a localization formula for the Poincare polynomial of the core of the flag variety, or the flag variety itself. So you end up with an expression for the Coulomb branch Hilbert series of TSUN in terms of Poincare polynomials of the Quasimodo moduli space. And these generating functions were computed by Nakajima in a paper called Finite W Algebras and Handsaw Quivers. So we can import the result for the generating function, combine two of them, and they glue together to give the familiar Coulomb branch Hilbert series. So that's one application of this geometric interpretation. Okay, so 3D equals 4 theories enjoy this duality called mirror symmetry, which is an R duality, and in particular exchanges the Higgs branch and the Coulomb branch of the theories, and masses are exchanged for their phi parameters. And yeah, all observables should match across this duality, and in particular, boundary conditions should also transform between two mirror dual theories. So yeah, it's expected that Neumann boundary conditions are mirror dual to Dirichlet boundary conditions, but it's a little bit of a question mark about what the dual of an exceptional Dirichlet boundary condition is. But yeah, there's evidence that it's true that the exceptional Dirichlet boundary condition of theory X can be expanded in exceptional Dirichlet boundary conditions of theory Y, where the transition matrix is this so-called elliptic stable envelope. But there's a particularly simple, the Verma character limits, this transformation is particularly simple, and the U matrix series turns out to be diagonal, or at least we've observed this in some examples. So this means that in a fixed vacuum, the Verma characters of theory X can be identified with Verma characters of theory Y. And this exchanges perturbative and non-perturbative contributions because in one of these limits only vortices survive, and in the other limit only the one loop piece survives. So we can see that explicitly in the TSU2 example. So yeah, this is self-mirror dual, so it's a little bit trivial in some ways, but if you take the half index of theory Y and you consider the A limit, this in this notation corresponds to sending T to 1, then this just becomes 1, the one loop piece vanishes, and you have a geometric series in the topological fugacity. On the other mirror dual side, you compute the half index, and the B limit here corresponds again to T to 1, and in that case, the vortex sum becomes trivial, becomes 1, and only the one loop piece survives, which telescopes to 1 over 1 minus, oh sorry, I've written Z here, it should be X. So it telescopes to 1 over 1 minus X. And yeah, that's just a resummed version of the geometric series on the left. So from the geometric prescription I gave from the blocks a few slides ago, then you can lift this to a general statement about A limits and B limits of the half index, because the A limit of theory.
You should have two vacua in this case, right? Why? I mean, I don't.
Sorry. So yeah, yeah. Okay, that's a little bit confusing. This is really, yeah. The vacua acts by exchanging in this notation x to 1 over x or zeta to 1 over zeta. Yeah, that's. So for example, in this, yeah, I should have an alpha label there. You're right. It's a little bit confusing.
So y and x are mirror theories, right? And then they also carry a label for each vacuum. I mean, I think we understood a while ago that these blocks, say if you have the blocks of theory A, they just become linear combination of the blocks of theory B. And actually the matrices usually are just like Stokes matrices. They correspond just to
Yes,
Stokes.
exactly.
Yeah, but now you are referring to a particular vacuum. I mean, why you don't have the label for each vacuum?
So in that limit, so in this simplifying limit, the Verma character limit, these Stokes matrices that you talk about become diagonal.
I see. So it is true for each vacuum, this statement that you're making.
This is for each vacuum, exactly. Okay. Yeah.
I see.
So it's a statement that, yeah. So maybe this general statement might be clearer, because I should have still put in a vacuum label, but it's the same on both sides. So here you have a particular vacuum alpha. You count the fixed points on the vortex moduli space of theory Y, and then you have the same vacuum alpha on the dual theory. And instead on this side, you only count the perturbative contributions. But yeah, you're right. There should be a vacuum label, but in this Verma character limit, it's this upper triangular transformation is just diagonal. Okay.
Sorry, can I ask a question?
Yes.
What's this n plus alpha?
Sorry, yes. So the n plus alpha is, yeah. So once you fix a chamber of mass parameters, and ordering on your mass parameters, at each fixed point, you have some attracting directions in the tangent space and some repelling direction. So this n alpha is the attracting subspace of the tangent space for each vacuum.
I see.
And when I write, when I write the persistent exponential of n alpha of the Coulomb branch, I mean the persistent exponential of the character of that tangent space subspace at that fixed point.
Okay.
So in this case, it's 1 over 1 minus z.
Okay.
Yeah. Okay. So yeah, recap of this last part. So I've discussed how the twist index computes, or that the A and B twist indices compute a Hilbert series of the Higgs and Coulomb branch. I've shown that if we factorize the twist index, then we can obtain a nice formula for the Coulomb branch Hilbert series in terms of the geometry of quasi-maps to the Higgs branch. And yeah, maybe I should have said a bit more in this previous slide. So in this specialized limit, the vertex function just counts the fixed points on the quasi-map moduli space. And you can view the mirror of this statement as giving a generating function for these fixed points. So here, each vortex moduli space only has one fixed point because it's just c to the power d. And then this is the generating function of those fixed points. So each order in Z, you get the number of fixed points of that quasi-map moduli space. Yeah, and you can make these ideas geometrically transparent for T-row theories, at least where we know that, say, the Q0 limit of the vertex function is a prime-square polynomial. Now, I was planning to discuss a slightly more complicated example, the 3D ADHM theory, but I think we're roughly...
Go ahead.
Is it okay to go ahead?
Yeah, please.
Okay, sure. Okay, cool. Yeah, good. So I want to say a little bit about a more rich example. So the 3D ADHM theory. So this is a 3D quiver gauge theory described by this quiver. And this is interesting because, well, for one thing, it's supposed to flow in IR to the world volume theory on M2 branes and be dual to supergravity on ADS4 times S7. And recent work by Choi and Huang has shown that the vortex partition functions of this theory exhibit some exponential scaling in n that accounts for some black hole microstates. So that's the motivation for studying this example. So in this first bit, I'm just going to talk about the theory with one flavor. And in that case, the Higgs branch is the Hilbert scheme of n points in the plane. And there's a torus action given by the R symmetry. So this is the T deformation, and also U1 flavor symmetry, because there's one hypermultiplet. Now the fixed points on the Hilbert scheme of points in the plane under this torus action are labeled by partitions. So if you have n, if the gauge node is n, then these are partitions of the integer n. And we label them by Young diagrams. Now, the quantized Coulomb branch algebra of this theory has been written down by Nakajima and Kadera, and they call it a cyclotomic rational Treadnick algebra, which I don't know a huge amount about, but I understand that it's some truncation or quotient of double affine Hecke algebra. And I've written the monopole operators in the corner here. Okay. And the Higgs branch algebra is generated by, as usual, gauge invariant polynomials in the hypermultiplet scalars. So in this case, difference from SQEDN is that there's an edge loop. Now, I don't have a quiver description for the vortex moduli space, but you can have there exists a description of the fixed points of the vortex moduli space, and so you can compute the vortex partition functions just as in SQED. Okay, so these formulae look quite complicated. I'm going to try and pick out the pieces to look at, but you can apply the geometric block recipe that I advertised in the earlier slides to this theory, and it gives you a hemisphere partition function. So the pieces to look out for are, on this theory, there's one gauge node, so one tautological line bundle. So in the Casimir energy term, you have this log zeta and log zeta. The terms proportional to log zeta come from characters of this tautological line bundle. And then the n alpha plus contributions to the Casimir energy are the terms proportional to, this term with the hook length and this term with the content. I should say what hook and content are. So the vacua are labeled by partitions. So each hemisphere partition function is labeled by a Young diagram. And then I'm taking sums over boxes of this Young diagram. So I have, for each box, I can write down the hook length, which is the length of this hook shape. And I also have arm lengths, which are horizontal lengths, and leg lengths, which for this green box are 0. So that's what these expressions are written in terms of. Okay, so you have classical piece or Casimir energy piece, which is determined by line bundles over the Hilbert scheme of points, and then a one loop piece, which is the particular exponential of the attracting directions at each fixed point. So here I've made a particular choice for the masses and the Fi parameter. In this case, there's one of each. I'm taking them both to be positive. And then the vortex function is the vertex, what mathematicians call the vertex, k-theoretic vertex function of the Quasimodt moduli space. And this was conveniently recently computed by Dinkins and Smirnov, so we can import that part of the computation to get the full hemisphere partition function. I'm not going to go through it today, but you can show that, we've checked that these hemisphere partition functions fuse exactly to twisted indices, 3-sphere partition functions, and the superconformal index of the ADHM theory. I should say as well that this vortex sum we showed is a sum over reverse plane partitions. So in other words, so a reverse plane partition is you take your particular vacuum of interest, so lambda, and then you add boxes on top of it to make a 3D partition that gets higher towards the edges of the partition. So this is a reverse plane partition built on top of this partition. And then the vortex numbers correspond to the number of boxes in this reverse plane partition. Okay, yeah, and then, yeah, I'm taking S is a box in lambda, and then pi S is that height above that box. So you can take the same Verma character limits that I've been talking about, and yeah, perhaps this might be a good answer to Sarah's question earlier, because now the vacuum dependence is more obvious, because on this side I have a partition lambda, and on this side I also have a partition lambda, and so these are Verma character limits of hemisphere partition functions in a particular vacuum. And so on the A limit side, this gives us a sum over fixed points on the quasi-map moduli space, which essentially just counts reverse plane partitions. The mirror limit gives us, so I mean, we take, in this case, it'd be taking something like U to 1 in the one loop piece. And it gives us product over the boxes in the base, and then 1 over 1 minus Z times is actually the hook length, or the arm plus the leg length of a box. And indeed, that's a well-known generating function of reverse plane partitions. Based on the general theory that we discussed earlier, that exceptional Dirichlet boundary conditions should yield Verma module characters, we expect that this object, at least when supplemented with Casimir energy, should give a Verma module character of the Nakajima-Kadera algebra. And from the fact that vortices are labeled by these reverse plane partitions, we expect there to be an action of this algebra on reverse plane partitions. Okay. I'll skip this in the interest of time. Okay, so I think this is the last thing I wanted to talk about, which is that we can also consider other boundary conditions. So I've been talking all the time about exceptional Dirichlet boundary conditions, but you can also consider a Neumann boundary condition for the vector multiplet. And the general principle is that these should yield simple modules of the Higgs branch chiral ring. So I'm gonna, in this part of the talk, consider the ADHM theory with P flavors now, and P is gonna be greater than 1. So the Higgs branch isometry group is SUP. And I'm also going to insert a Wilson line of charge n. So my local operators are not going to be gauge invariant, but they're going to transform under this particular representation of the gauge group labeled by n. So before I talk about the ADHM theory, I wanted to talk about a slightly easier analogy, which is the cotangent bundle to complete flag. So the first thing is that the Neumann boundary condition preserves boundary gauge symmetry. So when we set the gauge field to a constant value, we broke the gauge symmetry on the boundary, but now we have to integrate over gauge invariant operators up to the Wilson line charge. And so we get a contour integral form for the half index of the Neumann boundary condition. And for the TSUN theory, this is the particular operator count that you get. And this might be familiar from a localization computation on the disk, say, for a Neumann boundary condition as well. Now, when you take the Verma character limit of this formula, you end up setting, well, before you take the Verma character limit, you might recognize this as an integral form or a contour integral form of a Macdonald polynomial. So this is a Macdonald polynomial labeled by a partition specified by the Wilson line charge, and the variables in the Macdonald polynomial are the flavor fugacities. Now, when you take the Verma character limit, this sets equal the two parameters of the Macdonald polynomial, and you recover a Shor polynomial. And so the geometry of this example is that you're counting sections of a line bundle over the complete flag. And this is simply the Borel-Walbot theorem. And yeah, the local operators correspond to sections of this particular line bundle specified by the Wilson line charge over the flag. So we can do the equivalent calculation for the ADHM theory. So you write down the half index with the Neumann boundary condition, you take the Verma character limit, and then you can evaluate that integral. And you find something quite interesting, which is a Milne polynomial. So these are Milne polynomial I'm writing by Q dash, and the partition that labels it is the Wilson line. It's a rectangular partition with width specified by the charge n and height specified by the gauge group rank. And these are Q0 limits of a certain normalization of a Macdonald polynomial. And yeah, just as in the TSUN example, we expect that this half index is counting sections over this particularly simple Lagrangian submanifold in the ADHM quiver. So this is sort of the most naive Lagrangian you can write down, which comes from throwing away half the arrows of the ADHM quiver. And then you count sections of line bundles over this submanifold, and it coincides with this count of local operators. And yeah, so on general grounds, we expect this formula to be a simple module of the Nakajima and Kandera quantized Coulomb branch algebra. I was going to say something about the twisted index gluing, but since I've already gone over, I think I'll summarize. Okay, so we showed that hemisphere partition functions essentially coincide with holomorphic blocks, but you can give them a nice UV boundary condition prescription. Using holomorphic factorization and the fact that hemisphere partition functions compute Verma module characters, then we can obtain nice formulae for 3 manifold partition functions glued out of Verma module characters. We discussed the twisted index and the relationship between the Hilbert series and via factorization, Poincare polynomials of vortex moduli space. And I tried to show these ideas for a more interesting example of the ADHM quiver. I've talked a lot about the geometric interpretation of so the Q to 0 limit, but I think it'd be interesting to understand this Cardi limit Q to 1, which in this limit, the recent work of Choi and Huang, they show that the partition function or the vortex partition function accounts for black hole microstates in that limit. So I think that would be interesting to investigate the geometry of. Yeah, I'll finish there. Thanks a lot.
Thank you very much for interesting talk. Questions from audience?
Sorry, may I ask another question?
Yeah, please do.
So I would like to understand, so the object that you call H alpha,
Yes.
so the hemisphere block, I just wanted to understand how they relate to the holomorphic blocks. And because from what you're writing, it seems that if you define your hemisphere partition function with your Dirichlet boundary condition, you get exactly the blocks, maybe up to Q constants. If you use a Neumann boundary condition, you get basically the integral form of the blocks, if I understood correctly.
It's a particular Neumann boundary condition. So in this case, I've
that's
set
precisely the, I recognize the integral form of the blocks with the only condition that the phi is integer.
Yes, exactly.
So in general, you have this object that for the Dirichlet boundary condition is the holomorphic block. It's just another way to calculate. It's not different. I understand correctly.
Exactly. Yeah. The difference is that it's realized there's no topological twist. It's a partition function on a hemisphere with a boundary condition on the torus.
But
when you actually compute,
you are tailoring the boundary conditions so that they are in one-to-one correspondence to the vacua, which is
exactly.
So we are talking about the same object, just to avoid, to be sure. Okay, good. Thank you.
Yeah, definitely. Yeah, but this Neumann boundary condition is a little bit different because, so it's a little bit confusing because so often people write holomorphic blocks as contour integrals, but I don't think that's always possible. I think that's only possible when the Higgs branch image. So whenever you write a contour integral, as far as I understand it, that's computing a hemisphere partition function with a Neumann boundary condition because you're integrating over gauge fugacities, and that can only give you a a block if the Higgs branch image of that boundary condition coincides with these Lagrangian submanifolds. And for theories like TSUN or theories that are cotangent type or whatever, then you can write down a set of Neumann boundary conditions whose Higgs branch image coincides with these attracting Lagrangian submanifolds. But in general, I think the exceptional Dirichlet boundary condition works for any theory. It might be that there's, well, yeah, the Neumann boundary condition is like the mirror dual of these exceptional Dirichlet boundary conditions, but you have to put in some special matter on the boundary to select you the correct contour. I mean,
I don't know. I mean, my comment is that if you have isolated vacua, I think you can sort out a proper definition of the contour. What you are doing here, I mean, in the formula that you are showing for the when you have integer phi, then indeed you can do an integration on the circle because you have a meromorphic function. Whereas
it's a slightly different interpretation because for us this is Wilson line charge. But I think if you realize this is a partition function on the hemisphere, probably it's a quantized Fi, I suppose, yeah. But is it always possible to write down a contour for each isolated massive vacuum, or is that only true for I think that might only be true for theories where you can write where the Higgs branch image of the Neumann boundary condition coincides with these attracting submanifolds, but I could be wrong. I mean, I tried to do it for ADHM and couldn't.
I see.
Yeah, I'm not sure. But I think in general, exceptional Dirichlet should be mirrored to some Neumann boundary condition with some extra matter. And in that case, you can write it as a contour integral, but you have some quite complicated theta functions. Well, you insert basically the elliptic stable envelope inside the integrand.
That's right. I mean, when you have a non-integer phi, you should be factorizing this as well. So you would get a theta function instead of this power, and then you can calculate anyways your contour integral. I think then you understand this theta function as coming from matter on the boundary. I think this was also explained by Yoshida Sugiyama.
Yeah, yeah.
That's the correct way to think the Chern-Simons terms on the boundary. I mean, on the bulk, thinking that they are.
Maybe we should talk about this a bit more after, but I kind of suspect that you have to do something a little bit more complicated for theories that aren't cotangent bundles, whose Higgs branch is not a cotangent bundle, but I could be wrong. Yeah, thanks for the question.
Any other questions? Can you explain a bit about this Hanani-Ton Lagrangian?
Oh, sure. Yeah. So it's basically the simplest, most naive Lagrangian you can write down. So you throw away half the arrows from the ADHM quiver to get a half-dimensional submanifold, this a Kähler manifold. And yeah, I mean, I call it the Hanani-Ton Lagrangian because this first appeared in the papers called Vortices, Instantons, and Branes, where there it plays the role of a vortex moduli space, but for us, it's playing the role of a submanifold of the Higgs branch. And then we're counting sections of. So I mean, there's a tautological line bundle over the submanifold, and we're counting sections of that line bundle.
I see.
I mean, there's another difference with the TSUN theory in that you have this factor here. So if you turn off the line bundle, you still have some contribution here, and that's because this Lagrangian is non-compact. So in the flag case, this Lagrangian was compact, whereas this Hanani-Ton Lagrangian is non-compact, and so you have some non-trivial functions to count, even if you have zero line bundle charge.
I see. But in the case of theta flag, it's parameterized by partition lambda. If it is very broad, it should be parameterized lambda, right?
That's right, yeah.
Partition. But in this case, Lagrangian unique or not? It's not. This Hananiton.
No, I think that there's lots of Lagrangians. I mean, in particular, there's these attracting Lagrangians associated to vacua. So this is a special Lagrangian that's compact. I think it's the only compact one.
I mean, Hilbert point. If it is Hilbert point, I think it's just a zero image of this Hilbert-Chow map is compact one. That's my understanding.
But I think in that case, it's
wrong.
not. I think it's compact, but it's not Lagrangian anymore. I think the preimage of the Hilbert-Chow morphism. I think the Hananiton Lagrangian is not the preimage of zero.
Yeah, of course.
Yeah.
But its parameter, its partition, it's this, how to say, frac n is the somehow described Hananiton Lagrangian.
It describes the line bundle over the Hananiton.
Oh, line bundle. Oh, I see.
Yeah, sorry. So the math frac n is the. So there's a tautological line bundle, and then I'd take n powers of it. Math frac n power. Yeah.
Okay, I see.
So it's like the partition lambda for the complete flag.
Okay. Oh, I see. I understand what you mean.
And physically, it's the Wilson line charge.
Okay, I understand what you mean. Okay, I see.
So in this case, the boundary local operators literally parameterize sections of that line bundle.
Oh, I see.
But I don't know if there's any first principles derivation of the simple modules for this Deha algebra. I mean, I think this is a prediction of what they should be, maybe.
Okay, I understand.
I'm not trying to check that. I mean, it's kind of curious as well that this is a character of an SLN or Kirillov-Reshetikhin module. But that's a question I don't understand. I don't understand why that appears, really.
Okay, I see. But do you need to put some constraints on mass or FI parameter to get this module? It should be related to this partition lambda or this frac n.
There's no constraints. I mean, you have to pick a chamber at the start for your masses and FIs. In this case, just M is positive and the FI parameter is positive. And the Wilson line charge is positive.
I see.
But other than that, there's no constraints.
Oh, okay, I see. Okay, thank you very much. Any other question from audience?
So this quantization is without flavor symmetry, right? So quantized Coulomb branch.
In this case, there's no. In this case, I have p flavors, so there should be some SLP subalgebra, I suppose. I think. So,
but when you talked about simple modules, how do you specialize these flavor symmetry parameters?
I'm not specializing. I don't know a huge amount about this. Well, I know almost nothing about this algebra, but I'm imagining that there's some SLP subalgebra, the cartan of which is graded by these fugacities xi. But I could well be wrong. Some kind of horizontal subalgebra inside here.
Yeah, but I think people usually specialize the parameters, and if you take generic parameters, then this representation theory is something very simple, and somehow that is correspond to the fixed point in the Higgs branch. So I guess you are considering some special parameters. Maybe you don't put any flavor symmetry at all.
Possibly. Maybe we're calling different names. Yeah. I'm now wondering actually if I probably mean here more the Higgs branch chiral ring as well, actually. So that might be. Yeah, sorry, I think actually this is more a character of the Coulomb branch algebra of an affine quiver. with n nodes.
Oh,
Yeah, I've got this the wrong way around in the wrong mirror frame. This should be MH, or in other words, the Coulomb branch algebra of an affine quiver with n nodes and one. Or, yeah.
But then I think that the quantization is not too much studied in that case.
Yeah, that's a mistake. Thanks for pointing that out. Yeah. Okay, cool. Yeah, I was thinking, I've been working with P equals 1, where obviously these things are the same.
Self-mirror, yeah.
Thanks.
Any other question from audience? Okay, if not, let's thank Sam again. Thank you very much. Stop the recording.